In this video, we're going to take the concepts of functions and linearization that we developed in the last two videos and apply it to our epsilon log function from 2 videos ago. First, think about why epsilon log is not a linear function. So we can think of epsilon log as a composition of two functions. First, one that takes the displacement produces the length, and then one that takes the length and produces the deformation. In general, this is called function composition, as we see here. And we know from calculus how we can compute the derivative using the chain rule if we have composition of functions. So how do we approximate epsilon log by a linear function near u equals 0, i.e. for small displacements? We can use the linearization idea from the last video. So epsilon log of u is epsilon log of 0 plus the derivative d epsilon log evaluated at 0 times u minus u0. Epsilon log of 0 is 0. Think about y. And the derivative, as we saw in the last video, is the matrix of partial derivatives. In this case, it's a 1/4 matrix. Recall that epsilon log of u is given by this formula. Applying the chain rule, first we take the derivative with respect to little l, and then the derivative of little l with respect to u. We'll do this component by component, first with respect to u1x. So L of u, recall again, by the Pythagoras theorem from a few videos ago, is like this. So dl by du1x is just a straightforward application of computing derivatives. So you should try to do these derivatives yourself just to make sure that you understand the details of what's going on. Okay, and if we follow through, what we find that what it is simply minus of the cosine of lowercase theta. So the derivative of epsilon log with respect to u1x is minus cosine theta divided by L. And evaluated at 0, it's simply cosine of uppercase theta divided by uppercase L. Doing this for the other 3 partial derivative components, we get the matrix of partial derivatives at u equals 0 to be this, minus cosine theta over L, minus sine theta over L, and so on. So you should really do these calculations once yourself, just to make sure that we follow exactly what's going on. So for small u, that is u near 0, epsilon log can be approximated as this partial derivative matrix times u, which we can write like this. And let's see geometrically what this means. So if we take a member, okay, the first term in the numerator is the projection of the x component of the displacement along the member. And the second term in the numerator is the projection of the y component of the displacement along the member. So what this is the sum in the numerator is approximately the change in length of the member for small displacements, which we'll call delta of u. So for small displacements, the change in length of the member is approximately this matrix B times the displacement. So we can think of this matrix B as something that takes displacement and produces change in length. And this B matrix will be a very, very important idea in not just for this truss problem, where we've introduced it in a very simple way, but for mechanics problems in general, and appears over and over, for example, in finite elements and so on.